This video is about hyperbolic functions, which are even and odd combinations of exponential functions. We will define the 6 hyperbolic functions. I will also tell you why they're called hyperbolic functions after we discuss them a little bit more. And then we'll look at the graphs of the hyperbolic sine, hyperbolic cosine, and hyperbolic tangent functions. But before we even define them, let's look at some applications. You might say, why on earth would we care about even and odd combinations of exponential functions? Well, we care because they come up so often in physics and applications. So what you'll see is there are a lot of mathematical models out there involving decay or like the gradual exhaustion of some quantity or the absorption of some quantity. If we have a differential equation describing that quantity and then we solve that differential equation, the solutions of the differential equations can often be written in terms of hyperbolic functions. The most famous application of hyperbolic functions is a catenary, and that's just our name for the shape of a hanging wire. So if I have got two little poles like this and I've got some wire hanging between them, initially you might think that that wire is hanging, or that shape of that wire is like part of a parabola. And I wouldn't blame you. It does kind of look like part of a parabola, but it's actually not. It turns out that that wire will hang in this way. The equation for that wire can be written as y equals a constant a times the hyperbolic cosine of x over a. We also have a hyperbolic cosine function that's been shifted. If you've ever driven through St. Louis, Missouri, and you've seen the St. Louis Arch, that is based on a hyperbolic cosine function that has been transformed. Here is another mathematical model involving hyperbolic functions. It's a hyperbolic tangent function. This gives us the velocity of an ocean wave. If that wave has length L and that water has an average depth D, that velocity is approximately the square root of this function. G is acceleration due to gravity here, but we end up taking the hyperbolic tangent of 2 pi times the depth divided by that length, and then multiplying by this constant times the length, take the square root. That's how fast that wave is moving. And again, as we write these mathematical models that describe physical reality, when we solve those differential equations, we get results involving that involve hyperbolic functions. So that's why these are really important, and it's very important that you're familiar with these before you go on to Calculus 2 and Calculus 3 and differential equations. So let's talk about the hyperbolic sine function. The hyperbolic sine function is denoted this way. It looks like sine with an h of x, and it's defined to be this. It's 1/2 of e to the x minus e to the negative x. And it has a lot of properties in common with that trigonometric function sine of x. If I want to graph this, one way that I can graph it is I can graph y equals 1/2 e to the x and y equals negative 1/2 e to the negative x, and then add those two functions together, and then I'll get the graph of the hyperbolic sine function. One thing I'd like you to notice is that if you evaluate this at 0, you have 1/2 times e to the 0 minus e to the opposite of 0. So that's 1 minus 1. So you have 1/2 of 1 minus 1, which is 0. So the hyperbolic sine of 0 is 0. Just like the sine of 0 is 0, so that's easy to remember. And again, we can think of this as a combination of 1/2 e to the x and negative 1/2 e to the negative x. Now 1/2 e to the x looks like this, just roughly. when x equals 0, y equals 1/2 on that graph. Now, 1/2 e to the negative x goes the opposite way, but then I don't want 1/2 e to the negative x. If I distribute that 1/2, I want negative 1/2 e to the negative x. So I want to take that 1/2 e to the negative x, which goes down, and then I want to flip it. So what we're going to see is something that looks like this. Should be more symmetrical than that, but hopefully you get the idea. And hyperbolic sine of x is the sum of those two functions. Let's look at a couple of limits. The limit as x goes to infinity of hyperbolic sine of x is the limit as x goes to infinity of 1/2 e to the x, minus e to the negative x. Now as x goes to infinity, this part goes to 0. We know that, right? And so the hyperbolic sine of x approaches infinity. But I think the more interesting thing is to say it's approaching infinity, but it's also getting very close to this y equals 1/2 e to the x. It's not an asymptote because an asymptote's always a line. But in some limiting sense, the hyperbolic sine function is getting very, very close to this. In fact, it's always just a little bit less than 1/2 of e to the x. How much less? It's that much less, because you're going to take this value, and then you're going to subtract, we're going to subtract this value over here, or add that negative value there. So as x goes to infinity, what we get is a graph that looks something like this. Now as x goes to negative infinity, as you can imagine, we're going to have very similar behavior. It's not exactly the same, but it's very similar. As x goes to negative infinity, this is e to a large negative power. E to a large negative power, that's a very tiny fraction. That's 1 over e to a large power. So that's 1 over e to, or the 1 over a very large number. 1 over a very large number is a very small number. So this is going to go to 0. And this time, we've got a 1/2 times this negative exponential function. But as x goes to negative infinity, this is e to the negative x power. So that's a negative times a negative number. That's going to be a large positive number. So this is going to positive infinity. We multiply by -1, then it goes to negative infinity. We multiply by 1/2, it still goes to negative infinity. So the hyperbolic sine goes to negative infinity as x goes to negative infinity. But more interestingly, this is approaching 0, and the hyperbolic sine is always approaching this -1/2 e to the negative x. And in fact, it's always going to be just a little bit larger than that, because I'm adding that 1/2 e to the x, and that 1/2 e to the x is a very small number. So if I add this to this, it's almost like an asymptote, but it's not quite. Like this is going to get very close to this graph. It actually should be getting closer and closer. I didn't do a very good job in drawing that. Okay, so that is what the hyperbolic sine graph looks like. And notice hyperbolic sine of 0 is 0, which is very similar to sine of 0. And then it has this behavior. I didn't do a very good job in drawing it, but it turns out that just as the sine function is an odd function, hyperbolic sine is also an odd function. Remember what it means for a function to be odd. A function is odd if you look at the y values x units to the left and the y values x units to the right. So you go x units this way and x units this way, and you find the y's. So I go x units over here and I find the y, and I go x units over here and I find the y. I didn't do a very good job with my picture. But if I had, those y values would be the same but with opposite sign. So this y value and this y value are not equal to each other. They're opposites of each other. That's what it means for a function to be odd. This is for all x in the domain. Now, the hyperbolic sine function is an odd function, and you can prove that to yourself by replacing x with negative x and then multiplying the result by -1. You should get the function back. So let's prove it for hyperbolic sine. Oops. Hyperbolic sine of negative x is 1/2 of e to the x minus e to the negative x. But we're going to replace x with negative x. So we substitute a negative x there and substitute a negative x there. And a negative times a negative is a positive. Isn't that exactly the same as that, but in the opposite order? Instead of a minus b, I've got b minus a. So if I multiply both sides of this equation by -1, then I get 1/2 of e to the x minus e to the negative x. It's multiplying by that -1 takes that b minus a and flips it back to a minus b. So the negative sign of negative hyperbolic sign of negative x is hyperbolic sine of x. So that proves that this hyperbolic sine function is an odd function. So this is an odd combination of exponential functions e to the x and e to the negative x. And notice that the domain is all real numbers. I can put in any x value I want. It's going to work out just fine, because our exponential functions are defined for all real numbers. And then because I have this positive and this negative, the range is also all real numbers. The domain and range of hyperbolic sine are not like the domain and range of the regular sine function at all. That's okay. There is an analogy between hyperbolic functions and hyperbolas and trigonometric functions in circles that we'll look at in just a little bit. But the range is -infinity to infinity. It's all real numbers. So those are not analogous to the trig functions. Okay, so that's hyperbolic sine. Hyperbolic cosine is very similar. Looks like this. That's 1/2 of e to the x plus e to the negative x. So if I distribute that 1/2, I have 1/2 e to the x plus 1/2 e to the negative x. So when I graph it, I want to start by graphing 1/2 e to the x. On the other side, I want to graph 1/2 e to the negative x. Just trying to make it symmetric, but I don't know that that worked out. That's okay. It's the exact same function, just reflected across the y-axis. And let's evaluate this at 0. I get 1/2 of e to the 0 plus e to the opposite of 0. That's 1/2 of 1 plus 1, or 1/2 of 2. 1/2 of 2 is 1. So hyperbolic cosine of 0 is 1, just like the cosine of 0 is 1. Okay, that's cool. And as x goes to positive infinity, this guy approaches 0, and this guy approaches infinity. So the hyperbolic cosine approaches infinity because this guy goes to infinity and that guy approaches 0. But it's more important to think about how it approaches infinity. As it approaches infinity, this is e to a large negative power. E to a large negative power is something very small, so that's going to 0, and this goes to infinity. But we're getting very, very close to this function. Our hyperbolic cosine of x is always going to be just a little bit more than this value, and that little bit more is this. So we're taking this, and we're adding this little number, that little y value over there, and that's giving us that. Now, as x goes to negative infinity, then this would be e to a large negative power, so then this guy would go to 0. But if x is negative, this is a negative times a negative, so this is a very large positive number. So it's negative times a negative is a positive, so this would be e to a positive power. So as x goes to negative infinity, this goes to infinity, and this goes to 0, so hyperbolic cosine goes to infinity, but more importantly, this guy goes to 0, and this guy doesn't. So the hyperbolic cosine is getting very close to this curve. It's almost like an asymptote, but it's not an asymptote. It's getting very close to this, and it's always just a little bit more than that, and how much more is it's that much. So I take that y value over there, and I add that to the y values on this graph, and I get this. And that is my attempt at a hyperbolic cosine function. That's 1/2 of e to the x plus e to the negative x. And I think we can all see that this is an even function. You see the symmetry about the y-axis? That's what makes it even. You go x units in this direction, find the y value, and you go x units in this direction and find the y value. At x and negative x, the y values are the same. You can also just replace x with negative x here. You have e to the negative x plus e to the negative x. It's going to be exactly the same as this function. So the hyperbolic cosine function is even. And I didn't prove it, but I just sort of talked through it. That's because if I evaluate the function at x and I evaluate it at negative x, the y values are going to be exactly the same. And I think we can all see that the domain is all real numbers. You can put in any x value you want. It's going to work out just fine. And the range, well, the smallest that it could ever possibly be is right here. When x equals 0, we get 1. And then after that, we end up adding those two values together, the value of that exponential and that exponential. So we always get something that's greater than 1. So the range of the hyperbolic cosine function is 1 to infinity. Okay. Now the hyperbolic tangent function is defined this way, and it looks like this. Remember that tangent was sine over cosine? Well, hyperbolic tangent of x is hyperbolic sine of x over hyperbolic cosine of x. And that is 1/2 of e to the x minus e to the negative x over 1/2 of e to the x plus e to the negative x. Those 1/2s reduce and we get this. Notice that if you substitute in 0 here, you get hyperbolic sine of 0 over hyperbolic cosine of 0. And that's 0 over 1, so we get 0. At 0, these functions have the same values as the corresponding trig function, which is nice. It makes it a little easy to remember. And I'm always interested in limits. I always want to know what happens to this function as x goes to positive or negative infinity. So let's look at the hyperbolic tangent as x goes to infinity. It's minus. Well, remember, as x goes to infinity, this is e to a large negative power. E to a large negative power is a number that's getting close to 0. The same thing is happening here. So in the limit, these guys are approaching 0, and we just get something that's approaching 1. So our hyperbolic tangent approaches 1 as x goes to infinity. Let's see what happens as x goes to negative infinity. As x goes to negative infinity, I don't know why I'm writing on an angle for some reason. As x goes to negative infinity, this is e to a large negative power. So these guys are going to go to 0. And then this will be a negative times a negative, which is a positive. And this is actually going to be a negative times a negative, which is a positive as well. So this is infinity, or negative infinity over infinity, but it's the same function. Like this function and this function are the same. The only difference is that negative 1 out front. So the limit's going to be negative 1. I didn't take care of the infinity over infinity in determinant form here, but I think we can see that if that goes to 0 and that goes to 0, I just have e to the x over the e to the x, which is 1. In a similar way, this over this is going to be negative 1. So as x goes to negative infinity, the hyperbolic tangent function, approaches y equals negative 1. And so the graph is something like this. I'm not sure about the concavity, but that's roughly what the hyperbolic tangent function looks like. Now, sine is an odd function and hyperbolic cosine is an even function. So that has some consequences for the hyperbolic tangent function. So if I evaluate the hyperbolic tangent at negative x, it's defined as hyperbolic sine over hyperbolic cosine. Well, hyperbolic cosine is an even function. So this and this are exactly the same. I go x units in to the left, x units to the right, I get the same y value. For the hyperbolic sine, it's an odd function. So if I go x units to the left and x units to the right, oops, that's x units in one direction, x units in the other direction. They are actually opposites of each other. It's not factoring, but a lot of students remember this as like sort of factoring out that negative. It's not factoring, but we can kind of think of it that way, if that helps as a mnemonic. So the hyperbolic tangent of negative x is equal to this, which is equal to this because of the even and odd properties of the hyperbolic sine and cosine. But this is the hyperbolic tangent of x times negative 1. So that's a negative hyperbolic tangent of x. So if I go x units to the left and x units to the right, the y values are opposite each other. This is true for all x in the domain. So that means that the hyperbolic tangent function is an odd function. And I don't mean it's unusual. I mean, you go x units over here, find the y value, and you go x units over there and find the y value. That's x and that's negative x. And those y's are going to have the same absolute value, but opposite SIGN signs. Okay, so now we've got 3 of our 6 hyperbolic functions. Hyperbolic sine of x is 1/2 of e to the x minus e to the negative x. Hyperbolic cosine of x is 1/2 of e to the x plus e to the negative x. Hyperbolic tangent of x is hyperbolic sine over hyperbolic cosine. And that's really how I think of it. If I wanted to, I could write it in terms of exponentials, that divided by that, and we reduce the 1/2. Can you imagine what the other 6 are? Hyperbolic cosecant of x is 1 over hyperbolic sine of x. And 1 over that fraction is going to give me a 2 over e to the x minus e to the negative x. Clearly, x can't equal 0 for this one. We've got to be careful on that one. And hyperbolic secant of x, since I'm relating secant and cosine, the derivative of, or the definition of secant of x is 1 over cosine of x. The definition of hyperbolic secant of x is 1 over hyperbolic cosine of x. So we get that. And hyperbolic cotangent is 1 over hyperbolic tangent, or if you prefer, hyperbolic cosine of x over hyperbolic sine of x. And you can just take that fraction and flip it if you want it in terms of exponentials. Okay, so they're defined in the same way that you would expect, knowing what we know about trig functions. They have some properties in common with trig functions, and in other ways they have nothing in common with the trig functions. These are not periodic functions. They don't repeat every 2 pi or anything like that. But hyperbolic sine of 0 is 0, and sine of 0 is 0. Hyperbolic cosine of 0 is 1, and cosine of 0 is 1. They're all defined in pretty much the same way that our trig functions are defined. Let's see what else. Hyperbolic sine is odd. The sine function is odd. Hyperbolic cosine is even. The cosine function is even. Okay. I think that's where our similarities tend to end. Now, our trig functions have identities associated with them. We know that sine squared of an angle plus cosine squared of the same angle is equal to 1. And one of the ways that we derived this back in trig was using our unit circle. We said if we're on the unit circle and this is our angle A, x is given by cosine of A, and y is given by sine of A. And as A increases, or t increases, or theta increases, depending on how you labeled that angle, that point moves around and around the circle. But since this is a point xy on a unit circle, x squared plus y squared has to equal 1. Or that's my x squared plus y squared equals 1. So all of these, all our trig functions are really intimately related to circles. And anything that's related to circles. So let's see how these hyperbolic functions are related to hyperbolas. Now, I'm not going to have you memorize any identities for your hyperbolic functions because they are very similar to your trig identities, but they're just different enough. The SIGN signs are wrong that all of your intuition is incorrect. So I'm not going to have you memorize them, but I do want to show you one identity and show how it relates the hyperbolic functions to a hyperbola in the same way that our trig functions are related to a unit circle. So let's look at the hyperbolic cosine function and the hyperbolic sine function and subtract them. Well, hyperbolic cosine is 1/2 of e to the x plus e to the negative x. And I'm going to take that product and square it. And then over here, I'm going to substitute in my hyperbolic sine. That's 1/2 of e to the x minus e to the negative x. And I want to take that and square it as well. So when I square this, I want to square the fraction and that binomial separately. 1/2 squared is 1/4. With this, I want to write it twice in FOIL. Over here, it's very similar. Square the fraction. So we'll square that 1/2 to get 1/4. Then we've got a binomial. Now, some sticklers about terminology might get onto my case and they'll say, that's not a binomial. That's not a polynomial function. You're absolutely right, but it behaves like a binomial. So I think of it as a binomial expression. I treat it algebraically like a binomial expression, even though the term binomial may technically only apply to polynomials. I think we all know what I meant. There are two terms there, or two pieces, which I can think of like terms. Okay, so I've got this times itself, this times itself. Now we're going to distribute. Maybe you want to take out the 1/4. First times first is e to the x times e to the x. Add the exponents. That's e to the 2x. Outer times outer. It's e to the x times e to the negative x. When you add the exponents, x plus negative x is 0. So it's e to the 0, and e to the 0 is 1. So outer times outer is 1, inner times inner is just like it. So I get 1 plus 1, which is 2. Last times last is e to the negative x times e to the negative x. Add the exponents. Okay, then over here, we're subtracting this. E to the x times e to the x is e to the 2x. That's first times first. Outer times outer. That's a negative times a positive. That's going to be a negative. E to the x times e to the negative x. Add the exponents. X plus negative x is 0. So I get a negative 1. And then I get another negative 1. So that's negative 2. And then last times last, that's a negative times a negative. That's positive. And then I've got e to the negative x times e to the negative x. Add the exponents and we get that. Distribute that negative. Do you see what's going to happen? I'll have e to the 2x over here minus that one. And e to the negative 2x here minus that one. And I've got 2 minus a negative 2, that's 4, times 1/4 is 1. That's 1, guys. The hyperbolic cosine of x squared minus hyperbolic sine of x squared is equal to 1. Now, it may have been a while since you looked at hyperbolas, but if your hyperbola if you have an equation of this form, if x squared plus y squared equals 1, that gives us the unit circle. That's a circle centered at the origin. X is here, and y is here. Now, if I want to parameterize this circle, which just means I want to represent that circle, I'm using a third variable. I can let x be equal to cosine of, I think I'm going to use t for my parameter, and that y be equal to sine of t. And then as t increases, we go around and around that circle, and that point that is at that location, it sort of changes location as t increases. We go around and around. So if x is cosine of t and y is sine of t, and we substitute that into this equation, we get cosine squared t plus sine squared t equals 1. Just as t increases, we trace out that circle, and we have this Pythagorean identity. Sine squared plus cosine squared is 1. It's just written in a slightly different order, right? Well, hyperbolas have two equations. Either x can be negative, the x term is negative and y is positive, or the other way around. I'm just going to show you the one where x is positive this time. Notice the similarity between that equation and that equation. They're almost identical, but that opposite sign changes things a lot. In algebra class, maybe in high school, probably in high school, you learned how to graph hyperbolas. And we'll review this a little bit at the end of Calc 2 so that you can use it to graph in Calculus 3. But this hyperbola actually has this form, or this, not form, but this shape. So there's my y value and there's my x value. Since the x is positive, the branches of the hyperbola open to the left and the right. So we've got a unit circle, and cosine and sine trace out that circle. If x is equal to cosine of t and y is equal to sine of t, we trace out that circle as t increases. Watch this. If I represent this point by hyperbolic cosine of t and hyperbolic sine of t, as t increases, we're going to trace out this part of the hyperbola. So as t increases over here, we just go around and around this circle. As t increases over here, we go from one part of the hyperbola, and then we just keep going up and up and up. So if I replace x with hyperbolic cosine of t and I replace y with hyperbolic sine of t, we get that identity that I just mentioned. That's hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Now, if you're trying to remember these identities, you might be stumped. You might be like, I'm always thinking that I should be adding those. Sine squared plus cosine is 1, so hyperbolic sine squared plus hyperbolic cosine squared should be 1, right? It's not 1. That's why we call these hyperbolic functions, because these are nice parameterizations, nice ways to represent tracing out this curve as opposed to tracing out this curve. And this curve is a hyperbola, so it makes sense that we would call it a hyperbolic function. Okay, so that's one hyperbolic identity that I'd like you to be familiar with. Now we've also got other hyperbolic identities. If I take this guy and I divide it by sine squared, we got another Pythagorean identity, right? Cosine squared over sine squared is cotangent squared. Sine squared over cosine squared is 1. 1 over sine squared is cosecant squared. So that was one of our Pythagorean identities. Now if I take the same equation and I divide it by cosine squared, We get cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared. And this over here is secant squared. And that gave us 2 identities. Well, we can do the same thing with this to get more identities. Let's take this and divide by hyperbolic sine squared. Oops. So we get hyperbolic cotangent squared minus 1 equals hyperbolic cosecant squared. See how similar they are, but they're just not quite the same. That different sign makes all the difference. That sign makes all the difference, but that sign makes sense. It comes from the hyperbola equation. If you're just trying to memorize identities, though, your intuition might be incorrect because you might be thinking this way, but it's actually this way. If I take this and I divide it by, let's say, a negative hyperbolic cosine squared, or actually let's just divide it by positive hyperbolic cosine squared, that's fine. Then we get 1 minus hyperbolic tangent squared equals hyperbolic secant squared. See the similarities? But there's that difference. That sign makes a big difference. SIGN sign makes a big difference. So I'm not going to hold you responsible for any of these. I just want you to know that they're out there. And I wanted you to know why these are called hyperbolic functions. Okay, it turns out that the derivative rules and antiderivative rules for hyperbolic functions are very similar to the derivative and antiderivative rules for the corresponding trig functions. So that's going to be a handy mnemonic as well, and I'll tell you about that in the next video.